This atom has an unstable nucleus. Any moment now, it may undergo radioactive decay. Any time now. Or it may not. We just don't know, as decay is a random event. We cannot predict when any single nucleus will decay. But we can say, if we have a large enough number of atoms, then decay will happen somewhere in a sample. If we time how long it takes for half of the atoms to undergo decay, we have a measure, half-life, of a rate of decay. You have just seen about half of the atoms decay, and it took 5 seconds. So the half-life is 5 seconds. How long will it take for half of the atoms that have not yet changed to decay? Did you say 5 seconds? Yes. In this case, the number of original atoms halves every 5 seconds. You could have a bucket of 100 dice, and after each emptying of the bucket, remove all the ones that show a 6. Repeat until you have about 50 dice left. How long did it take? That's one half-life. If you recorded the time it took for your sample of dice to halve each time, you would get a graph like this. Each halving of the numbers is one half-life. The graph shows 6 half-lives. Half-lives can be as short as nanoseconds or as long as billions of years. If we record the radioactivity of a material over time with a Geiger-Müller tube and a counter, then we can plot activity, or a measure of the atoms decaying, against time to get a graph like this. The graph is for the isotope iodine-131. Notice how the count rate halves every 8 days, so we say it has a half-life of 8 days. Can you work out the half-life of this radioactive isotope? This is the decay curve for carbon-14, which all living things contain. It has a half-life of 5,730 years. Atmospheric carbon dioxide contains a small but constant percentage of radioactive C14, made by the action of cosmic rays on nitrogen molecules. This enters all living organisms via photosynthesis and subsequent food chains. While living, levels are constantly topped up, but upon death, the amount decays away. The ratio of C14 to C12 gives us a way of estimating how many half-lives have passed since death. For example, if a lump of wood contains only 25% of the original content of C14, then the wood has been dead for 2 half-lives, or 11,460 years. There is a limit to how far radiocarbon dating is reliable. After about 10 half-lives, or 55,000 years, there is so little C14 remaining that measuring it with any degree of accuracy is impossible. Short half-life radionuclides are used in medicine, so the patient is safe to go home in a few hours after dosage, whereas nuclear waste has a half-life of many tens of thousands of years. Most of the world's population have some strontium-90 in their skeleton, which originates from the atmospheric detonation of atomic weapons, mainly in the 1950s and 1960s. It has a half-life of 29 years. It will take well over 120 years before it begins to vanish from the Earth. But don't worry too much. We all have in our bodies radioactive isotopes we take in from our environment. For example, bananas supply us with very small amounts of radioactive potassium-40, which has a half-life of just over 1 billion years.
So here's the equation for radium doing alpha decay to make radon, and the half-life for this process is 11 days. Our question is, if you start with a 120 gram sample of radium, how much will be left after 44 days? The first thing let's do is figure out how many half-lives 44 days is going to be. Okay, so one half-life is 11 days. So 44 days is going to be 4 half-lives. Okay. Now that we know it's going to be 4 half-lives, let's just make kind of a little chart and figure out how much we're going to have at each step. So we're starting with 120 grams. After one half-life, we'll have half of that. So we'll have 60 grams. Okay, that's the first half-life. Now a second half-life, we'll go from 60 down to 30, 2 half-lives. 3, we'll go to 15 grams. And now our fourth half-life will give us 7.5 grams. So 7.5 grams is how much radium we'll have left after 44 days. Here's our next question. Hydrogen-3, which is also known as tritium, undergoes beta decay to make helium-3. And this process has a half-life of 12.3 years. Okay, so an 80-gram sample of tritium decays, leaving 2.5 grams of tritium. How long would this take? Okay, let's figure it out by just making a chart like we did before. So we're starting with 80 grams of tritium. One half-life is going to give us how much? 40 grams. Okay, one half-life. Now we're going to do another half-life. Now it's down to 20 grams, 2 half-lives. Down one more, 10 grams. Another one, 5 grams. And finally, down to 2.5 grams. So that is 1, 2, 3, 4, 5 half-lives. Okay, so 5 half-lives. And how much does each half-life take? Each half-life takes 12.5 years. So we're going to do 12.3 years. So we're going to do 12.3 years times 5 is going to give us 61.5 years. That's how long this whole process would take. Here's the equation for thallium undergoing beta decay to make lead, but we don't know the half-life here. We're going to have to figure out what it is. So the question asks us, we start with 200 grams of thallium-207 here. After 20 minutes, there's only 12.5 grams of thallium left. What is a half-life of the decay process? As usual, let's make a chart that shows how much this is decaying. So we start with 200 grams. One half-life is going to knock us down to 100 grams. Now another half-life will take us down to 50 grams. Then we'll get down to 25 grams. And finally, a fourth half-life will take it down to 12.5 grams. So we have 1, 2, 3, 4 half-lives. 4 half-lives. Now it's said that this whole process to go from 200 grams down to 12.5 grams takes 20 minutes. And in that 20 minutes, there have been 4 half-lives. So to figure out the length of one half-life, we're just going to do 20, the total time, divided by 4 half-lives, which is going to give us 5 minutes for the length of one half-life.
Now the graph you're going to be shown always looks like this. And to work out the half-life from this is really straightforward. So pick a number on the graph. The sensible place to start, if you can, if it's a nice round number, is where the graph begins at the y-axis. So pick that number, imagine it's 10,000, and divide it by 2. So 5,000. If you go across from the y-axis, from 5,000 to the line of the graph, and then go straight down to the x-axis, you're going to read time there. And that time is the half-life. If that time passes again, a second half-life has passed, then the number of nuclei will half again.
Okay, here I'm starting. I can pick any point on the graph to start with. Pick a point on your best fit curve, go down to half, and go across. And the length again of that horizontal line gives me the half-life, in this case 2 days. And I can do that again at any point on my graph just to confirm 40 down to 20, which is half of it, and across still gives me 2 days. Okay, again, just make sure you're picking a point on your actual best fit line. Go down to half, which would be what's left after a half-life, and then go across, and the length of that horizontal line is your half-life. If you have to show your work on the graph, this is what it should kind of look like.